So this is a review of oxidation in Ellingham diagrams. Right off the bat, we want to establish three conditions. One, oxidation is the loss of electrons by metals to form oxides, nitrides, etc. It can also be ceramics going from carbides to carbide and oxides. So the second condition, Gibbs free energy of an oxide has to be less than the Gibbs free energy of the pure metal. So the copper oxide is going to be less than the copper. And then the second condition, there has to be sufficient transport or mobility within the oxidation product. You have to have enough oxygen packing onto the layer, in order to have a stable oxide layer. So what's going to be a point of focus here is that Gibbs free energy equals your enthalpy minus temperature times entropy, as established in our previous video, or y equals mx plus b, where b, your y-intercept, is going to be your enthalpy, and then your g is your y, and your slope is your entropy. Now, why it matters is because it has a positive slope because your entropy is slowly decreasing. And when it's decreasing, your Gibbs free energy is going up. And why is the entropy increasing? Because you're going from 2 moles of something to, from 5 moles of something to 2 moles of something. So you're going to less disorder. You could also look at it as you have 1 mole of gas, and gases, they occupy a lot of space. There's a lot of chaos going on, to no moles of gas. Now you have this compound. And so these are some questions that we're going to answer, knowing all that. Why are the slopes of these curves so similar? Because of entropy. As I just explained, is half nickel, half titanium more likely to oxidize than pure nickel? Yes. As we know, alloys have more oxidation resistance than pure metals. And it's going to be somewhere in between the nickel slope and then the titanium slope. And 3 is a nickel and nickel 90, titanium 10 more likely to oxidize than pure nickel? No, because of what I just said earlier, except the only difference would be that you would see the line closer to nickel. Because you have more of it, it wouldn't exactly be 50-50. So now it's asking, what is a partial oxygen pressure for a 1-to-1 CO to CO2 ratio at 1,000 degrees Celsius? And now you have a full-on Ellingham diagram with a bunch of reactions. It looks scary, but don't get overwhelmed. What you do, it's really simple. Just go up, find 1,000, bam, bam, bam. And so you intercept with the chemicals of choice. Okay. You put the point of interception, and then you see the 0 right here. You just gotta find the curve or the diagonal that aligns to it. So for your answer, you would get 10 to the negative 15. At what temperature are CO and CO2 in equilibrium? Easy. You just find the intersection of the two Ellingham diagram lines. It looks about 700. Okay. What is the Gibbs free energy for the following reaction at 1,000 degrees Celsius? So 1,000, find the y-intercept, looks about negative 450. For the other one, negative 390, and you take the difference. Okay. Is the slope for the reaction into positive or negative? Why? Where is that at? So 2, it's going to be an alloy version of your regular nickel reaction, so it's going to be positive. Why? Because all you do is add an alloy to your nickel. However, your entropy basically stays the same. The only thing that changes is your stability of your oxidation. Is the formation of CO or CO2 more exothermic at 400 degrees Celsius? This one's easy. 400. Let's see here. So you have this one on the bottom. Anytime it uses words like stability or which one is favored, you just look for the lower one. Lower gives free energy is always favored. CO2. So, CO2. Bam. If you have any questions, comments, if I did something wrong, let me know.